Our project is titled as Production Testing and Finalization of Selective Grade Materials. It is an analysis-based project in MMSM area of Visakhapatnam Steel Plant. It is done by P. Shankar Reddy and P. Charantej. It is done under the guidance of K. Radhakrishna and Syed Riaz. The main aim of the project is to find a problem in the area of MMSM and to solve it. The problem we find is the variation of a grade from the estimated grade. Introduction. Vizag steel plant is only integrated steel plant in India. It is located in Visakhapatnam, Andhra Pradesh, on the coast of Bay of Bengal. It occupies around 19,000 acres of land in Visakhapatnam. It has huge facilities and they have high production facilities. They have a turnover more than 3.1 megatons. The major production facilities of raw materials handling, coke ovens and coal chemicals plant, sinter plant, blast furnace, SMS and continuous casting department, rolling mills, thermal power plant, water supply, QA and TD. The major products of Visakhapatnam steel plants is pig iron. The steel products are blooms, billets, wire rods, reinforcement bars, rounds, equal angles channels of various dimensions. And the byproducts are Portula fertilizer, which is exclusively from Visakhapatnam steel plant, coal fractures, and coal chemicals and tar products, benzyl products, and other products like liquid argon, liquid oxygen, liquid nitrogen, etc. Coming to the project, there are various stages where the steel grade being changed based on its chemical properties or physical or mechanical properties, which result to name the grade into another one. For example, at SMS level, Fe550D is taken and is set to various temperatures at furnace, and it is operated in rolling mills, and after cooling, we may receive any another grade like IS28230 or Fe555D or 1018 or Fe550. This is a main problem Vizag steel plant is facing. The MMSM stands for medium merchant and structural mill. It starts with furnace. At furnace, they maintain different temperatures for in different rooms. Based on the carbon percentage, the zone level is maintained. For low carbon and mild carbon steels, that is for carbons for less than 0.3% in the product, the zone temperatures are maintained as shown in table 1, and for medium or high strength steel, that is the carbon percentage in between 0.3 and 0.5% is shown in table 2. Rolling mill trains. This is the next level of the MMSM. After the product is heated in furnace, it is passed through the rolling mill trains. The rolling mill trains is divided into 3 types: RMT, FMT and IMT. The RMT stands for roughing mill train. It consists of 1.4 bar pressure for rounds and billets, and 1.45 for any other structures like channels. And in IMT and FMT, water pressure is similar. They maintain a water pressure of 1.45 bars for rounds and billets and 1.9 bars for other structures. In RMT, there will be a guide to change the product structure after reaching the FMT. The temperature of the bloom, that is the bar or the product formed from the rolling mills, the temperature will drops to 300 degrees Celsius when it leaves FMT. Then it enters the cooling bed area where the product is cooled to room temperature. A sample from this product is extracted and sent to central laboratory for mechanical testing. After seeing various slicers, cutters, they they will be products will be sent to packaging area where the products will be tested. In steel plant, they use a simple testing called spark testing. By seeing the sparks, they will estimate the final grade. That is, for high carbon steels, the sparks will be brighter, and for low carbon steel, it will be different from them. For every grade, the carbon percentage will be different, and the sparks will be different. Steel laboratory or SMS laboratory. SMS stands for steel mill shop. Here, the chemical analysis of steel takes place. The chemical analysis is called as a bath analysis. Here, the sample is collected and taken to ARS, organ rinsing station, and then based on the reaction, the properties are estimated, and based on the chemistry of the product, they will add some chemicals adjustment, that is adjustment to ferroalloy to take the desired grade, and then they will test the sample again. In mechanical testing laboratory, a small piece from every steel bar is which is taken from cooling bed area will undergo tensile testing. Here, yield load, ultimate tensile load, a percentage elongation is noted. Dimensions are also of the product also noted. Based on the formulas, IGL equal to 5.65 root A naught, where IGL stands for initial gauge load and A naught stands for area of cross section, and percentage G stands for percentage elongation, and FGL stands for final gauge length, and IGL stands for initial gauge length. And percentage elongation is equal to final gauge length minus initial gauge length divided by initial gauge length into 100. As we see this table, the heat number, which is the identity number for every product, and it is dimensions. And the defective product, which is marked in red, we can observe that the AML grade is N8T, but the final grade is N8DS. That's why it is rejected. In this one, we can clearly see that aluminum percentage is a little low. That's why its properties are changed. Similarly, when you see this another one which is marked in red, it is estimated as N80, but the final grade is N8. Here you can observe that manganese percentage is low. That is why that is change in the product. Luckily for 1018, they don't have any defects, but for 1020, you can see a defect is marked in red. Here comes the graphs for a, a graph is plotted between the grade and percentage elongation. A grade means final grade of aimed grade, that is which is changed or the properties are studied. You can see the elongation percentage in this graph. Similarly, the various parameters for angles, you can observe this 41, 45, 95 heat number doesn't have any chromium, but its grade is same. This implies that variation of the chromium may not affect the PRG grade, but if you see this 414584 heat number, the emerald grade is different and final grade is different. Coming to here, you can see that emerald grade is 1018 and final grade is ERG. And then similarly, like before, in 414424 heat number, cesium is missing, but here you can see that the emerald grade is changed from final grade. Similarly, a graph is plotted for angles showing grade versus percentage elongation. Various parameters for channels. Luckily, steel plant is not facing problems with channels. Only one or two products are defectives from out of 100. See, we can have only one defect here. The graph is so constant compared to other graphs. By implementing a cooling bed area, a proper cooling bed area before the cooling bed area, that means by providing a water bed for this rod to pass through, improves the cooling rate. In larger steel plant, they are maintaining a lower cooling rate, and that's why they are getting the defective products. At lower cooling rate, the chemicals will burn out. When it is higher, the hardness will be high. They are maintaining less than 35 degrees Celsius per second. If they tries to improve that cooling rate, they will get a final product. After taking a few samples and after doing some testing from our prototype, we have the graph plotted. Conclusion: by implementing a water bed, we can improve the cooling rate and thus improving the hardness and thus decreasing the defective products. If the VSP improves this condition and maintain zero human error, they will attain 100% of production without defects, that is without defects.